Yes, as you said, I want to present about some results from an experiment I have done some years ago. Find out how demand side can or cannot react to price signals. And if we speak about demand flexibility in a power system, at least I look on it in two different ways. You either can buy or utilize flexibility via markets. A lot of research is done in this field. So like reserve markets or flexibility markets, local markets, yeah. And then you sell your flexibility explicitly. You say, I can deliver so much megawatt or megawatt hours, and then you get paid for it. And the other, what my research is focused on is price signals or implicit flexibility. And that means that the demand is responding voluntarily because they want to save money. So usually there are two kind of price signals that exist. It's the spot price for electricity and it's the grid tariff. And both can give price signal to say now it's expensive to use electricity and you should, if you want, reduce your consumption. But why is this relevant at all? I want to show two topics. The one is to balance variable production, and that is concerning mostly a spot price. As everyone knows, there will be more renewable production in the future and already now, and it will vary. And so it has to be balanced. And of course, you can build extra production, or you have gas power plants, or batteries, or hydrogen, and everything to balance it. Or you, in addition, or first of all, I would say, use price responsive demand. Because otherwise, all the other options are, at least until now, very expensive. And there, both concerns short and long-term flexibility. And with short-term flexibility, I'm thinking about shifting, for example, demand in a day or even a week, whereas long-term flexibility is really more energy question. So you have maybe several weeks, months, even years, too little energy. Like it can happen, for example, in Norway, if it's a dry year, then we have too little water. Or as it can happen in Europe, you have too little gas. And that is more long-term perspective of energy saving, whereas the other, which is more short-term balancing of fluctuations, let's say in a week. And the other is to increase grid utilization. Can play an important role because, of course, this transmission to a renewable society, it will need huge investments also in the grid. Now I checked the numbers for Norway, and there it is expected that due to new demand, not due to production, but only due to increased demand, they expect investments the next 10 years of around 9 billion Norwegian crowns per year. And 1/3 of this is the transmission grid. I only want to mention it since I work in Statnett. And price signals, for example, through a grid tariff, can incentivize them to lower your demand in peak periods. And therewith, since the grid is designed after the peak demands, then you can lower or at least postpone grid investments. And that would then be more short-term flexibility. Because the peak periods or the design periods, they are really short. It's not like that there is a 1 week peak. It's some hours, some days, each 10th year, so to say. And of course, everything, if you have enough money, you don't need this flexibility. you only buy more. I mean, you build more. But if you don't have price responsive demands, I only would say the energy transition will be quite expensive. And it's already expensive, but it will be even more expensive. So it's worthwhile to look into it. And I focused on Norwegian households in my research here, because there should be a quite large potential for Norwegian households. First of all, 76% of all households are on power contracts that are based on spot price. So they get the price signal from the spot price directly. In addition, smart meters are installed everywhere now, already since early 2020. So they only can really, their bill is really based on the price in an hour and their actual consumption in that hour. In addition, the other price signal is also in place now since last year. They started also dynamic grid tariffs that should also incentivize to flatten out your demand. And there's also a lot, not a lot, but there is a good share of flexible demand, or it should be, in households in Norway, because they use electricity for heating, hot water, and more electric vehicles. And all this is a kind of storage. Heating, space heating, you store the heating energy in the building. Hot water, of course, you store the energy in hot water. And electric vehicles, you actually have an electric battery inside the electric vehicle. So all of these, you don't have instantly, if you have a need for hot water, you don't have to produce the hot water at that instant. You can do it an hour before, 10 hours before. It depends on how large your water boiler is, for example. And the same for vehicles and heating. And the last one is digitalization, which has really come more and more now. So you also can get information quite easy now from your grid company or from your power supplier. It's easy to find information about your demand, what is the price each hour, and you can learn and try to adapt to that. And the research questions I looked into is what is the potential? What really can you get out of these households? And more important, since I'm more focused on the grid perspective, not on the renewable energy balancing perspective, can we trust it in grid planning? Because we really have to be sure. It's nice to see that maybe this year people are responding to the price signals from spot price or in grid tariffs, but maybe next year they don't. So how can we trust it? That it's a stable response that will be there also in 5 years when it's actually needed. So I try to estimate how much price response we can expect from households in the short term. And short term, I mean not like in the next month. I mean from short-term flexibility. So hourly shifting or reduction of electricity consumption. And then what factors affect this response? So I looked into different factors, everything from the price signal characteristic to also more external factors like auto temperature. And then I also digged into what is the actual nature of the response. So how do they respond? What kind of appliance or measures do they do? And has that, again, some side effects. For example, a rebound effect. And I have done this with a pricing experiment. And then, of course, you could ask why I'm using a pricing experiment if prices are so high. So I could only go out there and collect the data from real life. There are high prices, and we measure the demand of all people in Norway. And I could do some nice analysis. And the reasons were because at the time I was planning and studying the pricing experiment, the prices were not that high, and no one could know that it will happen. But also there are some method characteristics that are really nice. First of all, I can have full control of the price signal, so I can design it as I want. I'm not to have to wait that high prices occur or that high prices occur over a longer period or what I want to test. And it also allows for control groups. So I can actually have households that get the price signal and households that don't get the price signal, which gives a really nice comparison and good results. And in real life, you never have this, because then maybe everyone gets the price signal. And then you don't know if there are some other factors that also have affected these people in addition to the price. But I will include some results from real life also at the end of this presentation, if we have time. So to compare. As I said, I used an experiment, also known as randomized control trial, where you recruit some people, households, and then you, by random, they are either in control groups or intervention groups that get the price signal. And the people in the intervention groups, if they react to the price signal, they actually got paid out, or they get a rebate on their bill accordingly to their response and the price and the hour. So that was a real economic consequence for them. It was not only a game. And in addition, we had also surveys to find more about what kind of people are they, and do they have electric cars, how large is the house, do have a little bit more control on every possible background variable, also income, for example. And we tested, I don't remember, I think 14 different price signals, which we designed. And the price signal is always hourly changing prices over 24 hours, over one day. And a price signal is based on a price profile, as you can see here. A price profile means it defines how long and when the high price hours in the day were. So for example, here we have in the morning and afternoon, a little bit lower in the middle of the day, whereas here B is all day high prices, but not at night. And P, it's only 2 hours high prices, rest low prices. And then we also changed the price level. So how high is the price in these price hours, peak hours? Everything from 2 crowns per Norwegian, 2 Norwegian crowns per kilowatt hour until 30, to really get a range of estimates. And then each intervention group had around 20 experiment days, which were chosen wisely for me, based a week before, based on a weather forecast. So I tried to hit the coldest days, because then there also should be a lot of demand on these days, and it's most interesting to see how the demand responds on these days. Then I analyzed this data with a fixed effect model, as it is called, for panel data, and that only means you take a regression analysis, but you control for all kinds of variables. So, for example, I control for both time and geographic fixed effects. That means effects that have the same consequence or effect on the households at each time step. That can be usually people wake up at 7 in the morning, and that's an average quite equal for all the people. So at the time step from 7 to 8, the electricity consumption goes up. And it's not because of a price, it's only because of the time of the day. And then we also included geographic fixed effects. That's mainly the weather, which affects people in an area equally, in average. And then I also included group fixed effects, which means that a group or a household in average can have systematic higher consumption, for example, because they live in a larger house and all this kind of effects. And then finally, I have this most important part that says something about how much the price signal has affected electricity consumption. That's what I'm actually interested in. The rest is only controlling for other variables. And then I used this on the data from the pricing experiment, which included around 4,200 households with 6 control groups and 13 pricing experiments. They were distributed over all the country, the main cities, as you can see on the figure. And then it was run in late 2020 until March 21. And I also collected electricity data, of course, and we conducted a survey. In addition, we also conducted a survey with households that were not involved at all in the experiment, to also could compare if we had some selection bias, so that only people very interested maybe in electricity topics and demand response were part of the project. And then we get results that are amazing. But the normal population maybe is not so interesting. So we also asked the same questions to the population to compare the variables also with normal people, so to say, and to say something about the external validity of the results. And all the data will be published soon, this month, hopefully. And there are the results. First, I only have plotted here of one control group and one intervention or treatment group that got the high price 2 hours. Their demand. And you can see, hopefully something happened. It looks already graphically that maybe they have reduced their consumption. But of course, it's more interesting to make a full statistic analysis of it, what I've done with the model I have explained earlier. And there it shows that in average, regardless the price signal, they reduced around the electricity consumption with 2.9% in peak hours. That means in that example, in these 2 hours. But they also reduced their consumption with 2.2% the rest of the day. So, which I called here now treatment hours. So that's all hours on an experiment day, which are not peak hours. And then, of course, this was the average over all price signals. It's more interesting us to dig more into the different price signals, if they respond differently to them. And so here it's only plotted the reduction in the peak price hours. So the hours with the highest price and how much have they reduced their electricity consumption in these hours. As you can see, it differs a little bit from the lowest is here, minus 2.4%, until the maximum here is 6.7%. And it gives already a nice indication. It looks like there's a lot of similar response in these profiles, and also for all kind of price levels, because you see also here the colors are the price profiles as illustrated here down, and then if there are several columns, then it means we have tested several price levels. So this is, for example, 2 crowns. It says pay 2 crowns per kilowatt hour, and this is pay 15. It's 15 crowns per kilowatt hour. But still, even it's increasing the price quite a lot. The response increases also, but I would not say quite a lot. So you already can see some patterns here. But I looked more into it and tried to find out what is real factor that has an impact on the response. So first, I looked on the price profile and the price level. I looked on it together. So this figure shows the change, the difference in response compared to profile B. So B is the reference. It says, that's why it says 0%, because then the difference in response, of course, is 0%. And then it shows how the other profiles give more or less response compared to B. As you can see, the A and C profile, these two, they are quite similar as B. Nothing changed dramatically. But then the profiles of only 2 hours, it seems like they increase the response. Here with 1.6%. Everything equal. And I made the same analysis for the prices, which go from 2, 5, 10, 15, 30. The reference and this time is 2 crowns. And then again, it shows the difference in the response. And it seems like if you increase from 2 to 5 to 10 crowns, some slight indications that it's a little more response, but it's not statistically significant, because you can see the confidence interval here. The lines are the confidence interval. And if they cross the 0, it's not statistically significant. But if you come up at 15, 30 crowns, something is happening. Significant higher reduction in electricity consumption. Then I also was interested to find out what happens if you, it's maybe a difference if you get a price signal each single day, for example, or only each second week, 1 day. How does this affect the response? And in my experiment, I had a different number of days between the experiment days. So I could check afterwards. If 0 means here, then write that there was an experiment day right the day before. 1 to 6 means it was 1 to 6 days between the experiment day, which is now, and the response today, until the last experiment day. And then we even have 7 to 19, so it means we even had some experiment days. That was 19 days ago that they also got the price signal at the next day. And it seems like there is a slight increase as longer the distance is with, or the period is between experiment days. But I checked also if the difference is statistically significant. It isn't. But at least we have an indication of an increase. So it seems like it's better to give people a break and not bother them each single day. Another factor which can have an impact on the response is, of course, outdoor temperature, because it's directly linked also to the demand and to heating, which is a flexible demand source. So I plotted the response for each temperature interval, starting at -20 until -15, and so on until +10 degrees. And it does not go higher because the experiment was in winter. So it means there was no temperatures higher than 10 degrees. And temperature is here measured as a 24-hour moving average. And yeah, if we first look here, it looks like warm temperatures, you get less response, or even no response. And at very low temperatures, it's more uncertain because we have less data observations. So we have a huge uncertainty and a huge confidence interval. But it also seems the estimates are slightly worse than in the range of -10 until at least 0 degrees. But I cannot say something significant about it. And then, as I mentioned, how can we trust the response over time? Meaning, is the response the same in the first month, like in the fourth month, like in this experiment? So I put it here. The number of an experiment day, if it was the first, the second, until the 20 ones, because it was around 20 experiment days per group, and plotted the response for each. Again, the first day is here, so that means on the first experiment day, the households on average reduced their consumption with 2.8% in the peak price hours again. And then we have 2 to 5, and that was then January 21. Mostly they reduced more, with 3.4%. But that's the highest response. And then it goes back a little bit, but flattens out, I would say. It looks like it's then stable at around minus 2.6%, which is good. That means that it's not deteriorating or getting less and less and less, and in the end you don't have any response anymore. And it also indicates, because there are two opposite effects that can play here, and it's both the learning effect, so meaning first time you get the price signal and you should do something, you don't know what to do, what should I put off, but then after it was first time, second time you already know what to do, and that may be an indication here. First, the second time, and third, fourth, fifth time you have higher response than the first time. But then of course people maybe get bored, or I call it response fatigue, because you also have maybe to do better things in your life than checking this each day or each second day. So some will fall off or don't get interested anymore in responding, and that will lead to this decline again in the response. But the good message is that the fatigue seems to stable, so that's not going on, and that each month again 10% go away, and it's stable after 3 months. And now we come to the nature of demand response, and that means not how much they have responded, but more, and what affect the response, but more how they actually have conducted, so to say, or done their response, and what is the characteristics of this response. And an average, based on survey results, 48% said that they did active measures to respond to the price signals we sent it to them. And here it means also manual measures, because there was no automatic sending of price signals, and you could not connect it to your smart devices. And here's a list of what they have done and what was the most popular measures. And in summary, I would say a lot of things are related to heating, of course. It's quite cheap to use this. And that is then usually load reduction. So you put off, or you reduce the indoor temperature, you use maybe a wood stove instead of electric heating. All this leads to load reduction. But they also use the dishwasher and washing machine and tumble dryers to shift when they use them. So try to shift them away from the high price hours. And that is then, of course, load shifting. So that consumption doesn't go away, it only has to come another point in time. And what we also have seen is that the measures they have done they led to long-lasting reductions. Also on non-experiment days, with minus 1.6%, which means that even on days where they did not get a price signal, also they were non-experiment days, their consumption was 1.6% lower than in the control groups. And that can be due to that if you first reduce the indoor temperature, you don't change the program again the next day because it's not an experiment day. Then it may be you keep that temperature for a longer time, and then you have the effect on each day. The same maybe with a shift to other times your dishwashing. It seems like, at least for some people, they change their behavior and not only on the experiment days, but also on non-experiment days, also leading to this reduction on non-experiment days. And of course, since
Matthias, quickly interrupt.
Yep. Is my time off?
Yeah, can you finalize within the next minute so we have some time for questions?
Yeah, of course. I can only say there was no rebound effect, even there was load shifting. And I can say I saw in real life a higher reduction than in the experiment, around 9%. And the takeaways are that there is actually a manual demand response, so you don't need some kind of automatic response, but it's limited, because I would say this, what was it, 2.6% it's not amazing much. But an interesting observation is that this demand response leads to long-lasting reductions in consumption. And actually you see only a minor short-term response on top of that. And then very good message is also that this response is persistent over time. So it don't get less and less and less over time. And that's good, because then you can actually use it. Because you can trust that you also may have it the next year and the year after. And also quite a surprising result is that you need extremely high prices to really trigger extra response. In my experiment, it seemed like there has to be over 15 NOx per kilowatt hour. And it seems also that information increases the response. So to conclude with what is the relevance now for peak demand reduction and grid planning, I would argue it's, at least from the experiment results, quite low, because the amounts are too low. I mean, some single percent is not enough. But it seems like the demand response programs or giving price signals is still worth it, because you can trigger long-lasting energy savings, which is always nice to have. Yes, and then only I saw high reductions in real life, and I'm still not sure why. But it could be because it was more information in the media and everything, and people really got aware of it. And in addition, in my experiment, you don't lose money. You only can earn money, but in real life, you have to pay the high prices. And so there can be a loss aversion effect, and then you're more willingly to do something. Thanks. That was my conclusion.